Hello, this is Mr. Stansbury. I'm going to take you through some of the problems from the AE assignment. Okay, so we're going to start here with number 5. A flu virus spreads in a school. The number of people N infected after T days is given by this formula here. Find the number of people initially infected. Okay, so initially infected is when T equals 0. So if we plug in 0 for this T, we have N equals 4 times 1.332 to the 0 power, right? Anything to the 0 power is just 1, so this N equals 4 times 1. So the number of people that were initially infected was just the 4. Okay? For B, calculate the number of people infected after 16 days. So now this T is going to turn into 16. So N is going to equal 4 times 1.332 to the 16th power. So we get our calculator out here. We've got 4 times 1.332 to the 16th power. So after 16 days, about 393 people. About 393 people would then be infected after 16 days. Okay, C. There are 1,200 people in the school. Estimate the time it will take for everybody in the school to catch the flu. So now we want to know when N is going to equal 1,200. So 1,200 equals 4 times 1.332 to the T, right? So, excuse me, what we can probably do here is move this 1,200 over here. So let's just do this. Let's just subtract 1,200. And then we can put it in our graphing calculator because 0 will equal 4 times 1.332 T minus 1,200. Okay, we can put that in. Now, here's what I'm kind of thinking here. We're at 16. Okay, so we'll put the equation in here. But again, since this is at 16 days, we were at 393 people. This is going to end up being our x value is going to be way off the graph over here would be my guess. Okay, so we'll put graph here. Chances are we're not going to see anything. Okay, so that thing's just spinning. That means it's still graphing, and there's nothing there that shows up. So good news is we don't have to see the whole graph. We just want to see more of the x value. So what we want to do is go into the window. And we want to see a bigger amount on the X. So let's turn that maybe up to 50. And now we hit graph again. And now instead of only seeing up to 10, now we're seeing up to 50. So I'm predicting it's going to cruise through in here. Yep, there we go. A little closer in there. Okay. So now what we want to do is we want to find where this crosses. So back to y equals, I forgot to put in the 0 for the second equation. And now we graph, and there's the 0. Now we want to find the intersection of these two lines here, right? So we're going to do second trace, which is calculate. We want to find 5, the intersection. Okay. Right now the y is at 36. We can't see it on there. It's okay because we know it's on the blue line. So we push enter. Now it's going to go to the red line. We push enter again, and then guess. Yep, we want you to guess. And there it is at x equals 19.89. So for part C, it's going to be about 20 days for everyone to get that thing, right? And then for part D, for what values of T time is reasonable to use this model? Well, since there's 1,200 people in the school, it's not going to make any sense for it to go past 20 days because you can't have 1,200 people in a school and then have, like if we went to 21 days, it might be up to, like 1,500 people, but that obviously doesn't make sense. So what values of T is it reasonable to use this model? So T would have to be greater than or equal to 0 because you can't have negative time. And then probably you can put less than 20 or you could put less than or equal to 20. Either one of those would be just fine. Okay? Okay. Let's look at 7. Kayla deposited 5,000, I think that's euros, I can't remember, into an account. The amount in the account increases by 8% each year. Write a formula for the amount A of t in the account after t years. So basically, let's come up with a formula here is what they're getting at. Okay, so the amount after a certain amount of time will equal, she started with 5,000, and now we're going to increase it by 8%. So 8% is 0.08 as a decimal. But we also want to add in the original 100%, which is 1.00. So you add those together, we're going to put 1.08 in for our growth. Oops, not 18, 1.08. Because remember, this 1 keeps the original 5,000, and then this 0.8 is now adding on all the growth, okay, to the t. So that should be our growth equation, okay. Find the amount in the account after 2 years. So now we just put 2 in for t. So the amount after 2 years equals 5,000, 1.08 to the second, and the amount for 2 years. And again, you don't do anything with this 2. This a of 2 just means the amount at 2 years. That 2 is, there's no math involved with this 2. You're not going to divide both sides by 2 to get rid of it, to get just the a by itself. That's just saying the amount at 2 years. Okay, so now if we were going to do a bunch of these different calculations, 2 years, 3 years, 5 years, 10 years, something like that, then I would suggest this. I would suggest doing y equals, clearing that out. Did it go away? It didn't. Let's try that one more time. There we go. Okay, and I'm going to put this in here. So I'm just going to do 5,000. And then 1.08. You can actually just go through and calculate this on your calculator too. There's no problem at all with that. But if you're going to do a bunch of calculations, this is going to save you some time. So we're not even really interested that much in the graph. We want to go straight to the table. So we're going to do second graph, which says table. And then it's going to give us a graph of everything. At time is 0, there's 5,000. After 1 year, it's 5,400. After 2 years, 5,832. So this is 5,832. Okay. So that was for part B. Again, if you need more times on that, that's where this table can come in really handy. You know, how much do we have in there after? If they left it in there for 10 years, you could just go down, just keep scrolling down until you get to 10 years, and away you go. Okay. All right. Number 4, temperature of a liquid t minutes after it's been placed in a refrigerator is given by t. The temperature at a certain time is what that means, equals 100 times 1.02 to the negative t degrees Celsius. Find the initial temperature. So for part A, we have time, I got to do capital T, time at 0, sorry, the temperature at 0 is 100 times 1.02 to the negative 0 degrees, right? Anything to the 0 power, whether it's positive or negative, is just 1. So that means our initial temperature at time 0 is 100 degrees Celsius. Okay. Part B, find the temperature after 15 minutes. So now we'll just start plugging in time into that, because this is t minutes. So we get t of 15 equals 100 times 1.02 to the 15th. Now again, we're going to have 3 different things we can put in here. We could do the table, but since we've got 15, 20, and then 78 is way up there, let's try this. Another way to do this without having to re-enter everything in over and over and over again is simply put this into the regular calculating screen here. We've got 100 times 1.02 to the, and we have the 15th, right? So at 15th, it's going to be 134.6 degrees. So the time at 15 minutes, it's going to be 134.6 degrees Celsius. Although I just realized that's supposed to be negative 15. So scratch that. That's to the negative 15th because I forgot the negative t. So here's what we can do. We can go up and then we just arrow up and highlight that and push enter, and it will give you that equation back, so now you can edit it. So I want to do negative 15 instead of positive 15. And now we push enter. There we go. Now it's down to 74.3 degrees. Time at 15 is 74.3 degrees Celsius. Okay? So this was part I. I is time at 20 minutes is going to equal, instead of entering, well, I guess we can put the equation in there just so you know what it looks like, 1.02 to the negative 20th. So now a nice trick on this is if I go back up and I highlight this here, and I push enter, again, it will give me that equation back, and now I can edit it. So now all I have to do is go back and turn my negative 15 into negative 20, and I push enter, and now it's down to 67.3 degrees. So the time at 20, temperature, sorry, at 20 is 67.3 degrees Celsius. And then for part 3 on this, we're going to put in 78. So the temperature at 78 minutes is going to equal what? So go back up, highlight my equation, push enter, turn that negative 20 into negative 78. Push enter, and we're at, wow, all the way down to 21.3 degrees. Okay, so we've done that. And these here, sketch a graph of the temperature of T for T greater than 0 using A and B only. Okay, so they're saying basically draw ourselves a little graph here. So we really only need this portion of the graph, right? So we'll go up to 78. So let's do, like, say 10, 20, so forth and so on. And then on this here, we got to go up to at least 100, and then it's going to come back down, okay? So we can maybe do by tens on this one as well. Okay, so made our axes there. You want to make sure you label your axes, time in minutes here, temperature in degrees Celsius here, and you usually want to give it a title as well, temperature of liquid when put into the fridge. Okay, so let's graph these points that we have. At 15 minutes, at 0 we were at 100. So let's do this maybe in a different color here so it's easier to see. At 15, let's see, time at 15 was 74.3. So that's about right here. Time at 20 was 67.3 here. And then the time at 78, which is way over here, is at 21.3. So looks like it's kind of going like this. It's going to go down, and then it's going to just flatten out here, right? We don't know exactly where, but it's going to look something kind of like that, isn't it? Okay. And then let's see, part D here. How long will it take for the temperature to fall to 15 degrees Celsius? So that's where we might want to put this into our graphing calculator, because for part, so this was C over here, the graph, and then part D here, we want to know when 15 is going to equal 100 times 1.02 to what time. So we got to figure out what that time is. Okay, so we can put this into the graphing calculator. We can also do this as a logarithm, but we haven't quite gone over that yet. So let's just stick to the graphing calculator bit here. Okay, so here's what I'm going to do. Since this is going to be off my window already, I'm just going to subtract this 15 over. So I won't put 0 equals 100 times 1.02 to the t minus 15. Okay, so y equals, I'm going to clear that out, and we've got 100 times 1.02 to the t, which is going to be, it's always going to show up as x in your graphing calculator, minus 15. Okay, now I can graph this. It's not going to show me what I need to see because this is only going to go from normally what's like regular zoom, it's from negative 10 to positive 10, negative 10 to positive 10. We know this thing's going to go past 80. It's going to get up to at least 100. So here's what I'm going to do. I'm going to go into Window, and my X max is already at 50. I'm going to put that at 200 and see if that gets me close enough. Okay, and then we'll put graph, and I know it looks kind of weird with all that on there. But let's see where our graph we should see that thing come down here if I entered it in correctly. All we see is just a spinning light here. Not seeing anything. 1.02 to the x minus 15. Oh, part of the problem also is we want to know, okay, when that gets to 15. So we want to see when that thing hits the x-axis. So we got to figure this one out. Okay, so let's maybe put our x max on our window. Let's maybe go out to, I don't know, 500. That's a lot of minutes. But we can at least take a look and see if that thing ever crosses this x-axis when we want it to. Okay, just realized that yet again I forgot the negative on the x. So let's go. We got to go back. I got to go back in and fix that. So I believe I can just put the negative sign in there and it'll move the rest over. Let's see, negative x. Okay, now let's graph it and see. So that negative threw me off twice on this problem. There it is. It's way up here. So really our window is my window that I made is way too big. So let's go back and switch that just to make it look a little nicer. Okay, let's change that back to maybe 200. Okay, and then we push graph again. You know, you don't have to because you could already see it, but it just so that it looks a little nicer. Just for my own satisfaction. Okay, there we go. So it looks like it's pretty close to about 100. So let's calculate what it is. So we're going to do second trace, find the intersection. Ooh, except for I didn't put 0 in for the second equation again. Because remember we set that equal to 0. Okay, and then we hit the graph. Okay, now we do second trace, find the intersection. Oops. Which is right there. And then you enter, 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 and it's going to tell us that it intersects at 95.8. So t equals 95.8, and that's going to be minutes, right? Okay, so that's how long it's going to take. All right, last one, number 7. A group of turtles was observed in a lake in 2005. The population of turtles has decreased by 5% each year since. The graph alongside shows the population of turtles since 2005. State the value of A. And here it's from this equation right here is where we're going to try to state the value of A. So let's do this. We got population equals K times A to the T. A is the growth rate, K is the original population, okay? So A is going to be our growth rate. It says it's decreasing by 5%. So what we want to do is take 100%, the original, subtract the 5% that it's decreasing by, and that is 95%. So that means the A, K times 0.95 to the T, okay? So A is going to equal 0.95, okay? Find the value of K and interpret this value. K is this original amount, so that's this point right here, which it doesn't actually tell us what it is, but it looks like it's around 340 or so. But they're asking us to actually find what the value of K is. So instead of guessing by this graph here, what we want to do is we want to use this value here. That X is 1 and then Y is 323. So let's plug that into this info here. So the population is going to be 323 with K times 0.95, oops, to the 1, because that T, this is T, and this is P for population, right? T and P. Okay, So that's going to be 323 equals K times 0.95. So if we divide both sides by 0.95, that will tell us what our K value is exactly instead of roughly. Okay, so we get in here. Let's see, clear this out. And we get 323 divided by 0.95. And that tells us that our original population, hey, look at that, guessed right on the spot, equals 340. Okay, so K is 340. It says interpret this value. That is the starting population. Okay, make sure that you answer all parts of the question here. This is a question you will often see on a test, and I often get people that will figure out what K is and then they forget to interpret the value. So make sure you're reading the whole question. Okay. C, find the population of turtles in 2015. So this is a group of turtles observed in the lake in 2005, and it's decreased 5% each year since. So the difference between 2005 and now 2015 is 10 years. So that means T is going to equal 10 in this case. So for C, we're going to do P equals, we now know that K is 340 times 0.95 to the 10. Okay, so now we're just going to plug that into our calculator and figure out what that value is. 340 times 0.95 to the 10th power tells us that the population is going to be down to about 182 turtles. Okay. And then part D, do you think it's reasonable to apply this model for negative values of T? Explain your answer. This is a tricky one because when you go to negative values of T, that's negative time. But really that just means time before 2005. So there probably was turtles in there in 2004, 2003. Unless, like someone came in and brought a bunch of turtles in 2004 or 2005 or something like that. So I would say that it probably is reasonable to apply it for some negative values of T, but probably not forever and ever. Because if you go back, a long, long time ago, it would be that there's probably millions of turtles, which probably wouldn't be true. Okay. Okay, well, that's all we have for this here. Just to let you know, I just checked the answer in the back of the book for 7D, and they say no. This would be an extrapolation and therefore unreliable. That's possible. It's possible that it could work. It's possible that it might not work. So it really kind of is up to your interpretation. The book interpreted it one way. I interpret it a little bit differently, but either way is probably good. Okay, if you have any further questions about any of this stuff, please feel free to ask. Thanks.